Welcome back to Honors Calculus. In this video, as you can barely see behind my head, we're going to continue our discussion of the coordinate plane with some ideas of the elementary functions. Elementary functions, my favorite definition, is simply the functions that you learn about in algebra and pre-calculus courses. That is the algebraic functions, polynomials, rationals, radicals, absolute value, the trigonometric functions, sine, cosine, tangent, inverse sine, inverse cosine, inverse tangent, inverse secant, the exponential functions, the logarithmic functions, and the ones you probably haven't talked about previously, the hyperbolic functions. Many of those we're not going to get into until the second semester of calculus, but in this video, I want to just run through a brief review of the functions that you should be familiar with and a couple of properties of them. So let me get my head out of the way, and let's dive in with the simplest function first. The unit function, f of x, is constantly equal to 1, sometimes called the constant function. And we can graph this function by plotting a couple of points, pick a couple of values for x, -2, -1, 0, 1, and 2 spring to mind as useful things. And no matter what you plug in, the function spits out 1. So if we draw some coordinate axes here, and we pick and plot each of those points, and play a game of connect the dots, we get a graph of a unit function that looks something kind of like this. Categorization of functions that you're familiar with, the domain of the function, it can take on all real numbers without any issues whatsoever. The range is simply 1. No matter what you put in, it spits out the number 1. All right, moving onward. The identity function, my personal favorite function, can be given as f of x equals x. Whatever you put in, it spits back out that exact same thing. So if we set up a table of x and y values, and we pick a couple of values for x, like -2, -1, 0, 1, and 2, this thing is going to spit out exactly those values, -2, -1, 0, 1, and 2. So we'll sketch out some coordinate axes. We'll plot these points, -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. Draw the line connecting them, and we get the straight line forming a 45-degree angle in the xy plane. Right. Same questions we asked with the unit function, we can ask on the identity function. The domain of this function is from negative infinity to infinity. You can plug any number in and get something out. And the range is also from negative infinity to infinity. No matter what you want to get out, you can just plug exactly that in and get that out. So we're good to go. All right, moving right along. How about the squaring function next? The squaring function is the function f of x equals x raised to the second power. And once again, we can pick some values for x and y until we have a reason to do otherwise. I'm going to look at x as -2, -1, 0, 1, and 2. In this case, -2 squared is +4, +1, 0, +1, and +4. And you will notice I'm drawing the graph a little bit smaller because we're starting to get to the point where we need stuff to get further around. But we plot these points and we get a curve that looks something like that. You probably remember from previous coursework that this curve is called a parabola. You've probably seen them drawn much more nicely than the one I happen to have drawn here. But the domain of the parabola is all real numbers from negative infinity to positive infinity. No matter what numbers you want to square, you can square them and get a result. The range of the parabola goes from 0 to infinity. Whenever you square a number, the result always comes out positive unless you started with 0, in which case the result comes out as 0. Continuing on, the cubing function f of x equals x to the third power takes the squaring function and is even more extreme. So if I plug in some values for x, -2, -1, 0, 1, and 2 yet again, well, -2 cubed is -8, -1, 0, 1, and +8. And let's put this really in close so I might have some space on the side to continue my discussion. Let's plot these points. And you get a curve that does something kind of sort of like that. Once again, the domain of the cubing function goes from negative infinity to infinity. There's nowhere where something weird happens in the cubing function. And the range, once again, gets positive and negative values. So the range here is also from negative infinity to infinity. Right. Continuing onward, let's take a look at the reciprocal function. F of x is 1 over x. And you will notice on this function, when I set up my table, as reasons you probably remember from previous courses, I'm going to throw a couple of extra values in. So in addition to -2 and -1, I'm also going to look at -1/2 before I get to 0, and then 1/2, 1, and 2. The reason for that is when you take the reciprocal, you end up with -1/2, -1, -2. The reciprocal of 0 is undefined, and then you get 2, 1, and 1/2. So taking my graph and going back to the zoomed in version we were using before, we can plot these points. -2, -1/2 is somewhere around there. -1, -1 is there. -1/2, -2 is about there. And then we have here, here, and there. And you probably remember from a previous mathematics course that at x equals 0, we have what's called a vertical asymptote. We will talk more about vertical asymptotes and look into how we define vertical asymptotes in a very clear manner in the next couple of weeks. But for now, let's just sketch out the graph as we are familiar with it. You're going to end up with something that looks kind of like that over here and does kind of the mirror thing over here. And the shape of this curve is called a hyperbola. If you have studied conic sections in a previous class, you've probably seen hyperbolas where the axis went this way instead, but it's the same shape, just kind of tilted 45 degrees from the hyperbolas that you traditionally study in the discussion of conic sections. For those of you who are moving onward, we'll talk more about what it means to be a hyperbola in Calc 3. The vertical asymptote that I mentioned, we will talk about more in a later lesson when we give a formal definition of what a vertical asymptote means. But for right now, we'll stick with analyzing the domain and range. And the domain and range of the reciprocal function are any real value except 0. Generally, we'll write that in interval notation as the open interval from -infinity to 0, union with the open interval from 0 to infinity, and we'll use exactly that as well for the range. All right, up next, the root function, f of x equals the square root of x. quick table of values. One of the things you'll remember about the square root is it's not defined for negative numbers. So I'm just going to start at 0, 1, and instead of going to 2, let's jump all the way to 4, because that's the next number that has a very nice square root value. Plotting those points, playing the game of connect the dots, the square root function has a graph that's kind of a half parabola turned on its side. The domain and range of the root function are both from 0 to infinity, closed at 0. Right. Now we go on to some of the transcendental functions in trigonometry. Right. The sine function, given as sin of x, you'll remember from previous coursework that you can measure an angle in either degrees or in radians. For our purposes in this course, we are exclusively going to use radian measure. It is far more useful analytically. But you'll probably remember the key points. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. I'm not drawing the x and y axis to scale in this particular graph. Honestly, the vertical axis is about 3 times as large as it probably should be, but I'm using that to get a nice looking picture. Right. But the sine function or the sine wave has the nice property of being a periodic function, which means that this shape just repeats over and over and over again. Right. The sine function has a period of 2 pi. We'll talk a little bit more about periodic functions in the next lesson. Right. The sine function also has the property of its range is between -1 and +1, closed interval, including those 2 endpoints. The sine function is a nicely bounded function. The sine function also has the property of the related function, the cosine, cos of x, is the sine of the complementary angle, right? Cosine means complements sine. So the complement of an angle to angles add to be pi over 2. So we take pi over 2 minus x, and that gives us the complement cosine. So we can look at that without having to draw a separate graph. Instead, I'm going to move on to the next trigonometric function that has a unique graph, that being the tangent function. Right. The tangent function, you probably remember being graphed on a truncated interval. So we'll go with negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2, which is 2 pi over 4. And the graph has a vertical asymptote at pi over 2 and at negative pi over 2. But otherwise kind of just snakes through. And then it is also periodic, so it's going to repeat and drawn probably a little bit better than I draw it. But the cosine function, or I'm sorry, the tangent function has a period of pi, unlike the other trig functions that have a period of 2 pi. The tangent function is important because it is the best defined inverse function. Arctan of x is defined that y equals arctangent of x if and only if x is the tangent of y. Not x, y. So because the tangent and all of the trigonometric functions are periodic, we have to restrict domain and range in order for things to work. The arctangent function is nice because it really goes everywhere, but you take the nice graph of the tangent, you kind of put it onto its side. You're going to end up with horizontal asymptotes at negative pi over 2 and at pi over 2. And then at pi over 4, 1 and negative pi over 4, negative 1, you'll have a couple of key points. And of course, 0, 0. So take that tangent curve, turn it on its side. That's the thing we call the arctangent. Those are the functions that are going to be of the most use to us. I will mention the other trigonometric functions, right? The secant and cosecant, which are the reciprocal of cosine and sine. The cotangent, which is the tangent of the complementary angle. And of course, each of those has an inverse function: arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant. We won't make too much use of those. For those of you moving onward to Calc 2, in Calc 2, the secant becomes a very important tool along with the sine and the cosine and the tangent. We'll see a little bit of why later on in this course, but that's something that really gets built on in the next course in the sequence. So that's a quick library of elementary functions, some of the important functions that we're going to play around with throughout the course. You should be familiar with all of those functions already. If not, take some time and review them before we move onward. And one property that works nicely with functions is that we can classify functions as being even or odd. A function is even if the value of a function at x is the same as the value of the function at the opposite of x for every value of x. A function is odd if the value of the function of x is the opposite of the value of the function at the opposite of x for every value of x. It should be noted, most functions are neither even nor odd, but if you can identify one of these properties, it can make working with that function a lot easier. As a quick example, if I consider the function f of x equals x squared minus 1. Well, if I evaluate f of the opposite of x, that would be the opposite of x squared minus 1. And the opposite of x squared is negative 1 squared, which is 1 times x squared. So this is the same thing as x squared minus 1, which is f of x. So we can conclude that this function is even. As another example, let's consider g of x as, say, x minus 1. If we evaluate g of the opposite of x, we get the opposite of x minus 1, which is just the opposite of x minus 1. That's not what we started with. That's not the opposite of what we started with. G is neither even nor odd. There are a couple of theorems in the typed notes on even and odd functions. For the sake of time, I'm going to skip over the proof of the first one. But I do want to state it because it is some useful properties. If you have two even functions, f and g, then when you multiply them together, you get an even function. And when you add them together, you get an even function. If you have two odd functions and add them together, the result is odd. If you have two odd functions and multiply them together, the result is even. And finally, if f is odd and g is even, then f times g is odd, but f plus g we can't determine. If you have an even function and an odd function and you add them together, it's possible you end up with an even function. It's possible you end up with an odd function. It's possible you end up with a function that is neither even nor odd. The proof of this theorem is presented in the typed notes. For the sake of time, I'm going to jump ahead to the next theorem and just state it as well, but I do encourage you to take a look at those two proofs. They are fairly interesting. The other statement is the function f of x equals x raised to the n power. And this function is even if n is even, and this function is odd if n is odd. That's how the ideas of even and odd functions got their names. All right. So again, please do read over the proofs of those two theorems as presented in the typed notes. But what I want you to look at here is, let's take a look at this more complicated polynomial function. F of x equals 4x to the fourth plus 3x squared minus 9. I would like you to first use the properties of those two theorems to determine if this function is going to be even or odd. Using what we said about the function f of x equals x to the n, see if you can rewrite this function as simpler functions in terms of x to the n being added together or multiplied together. Then determine if that result is going to be even or odd, and then use the definition. Evaluate f at the opposite of x and verify that this function has the property you claimed it would. Write that one out, see what you get with it, and I'll see you in the next video.